The question is, could you do an example on finding the centroid of a 2D section with a hole? This is the problem that I have chosen here. We have a 2D plate ABCD with a hole E like shown in this picture. The question is to determine the location of the centroid of this section x bar y bar with respect to the 2D xy Cartesian coordinate system shown in the picture. The approach that I want to take here is to treat the plate as a composite shape consisting of standard shapes. We see three standard shapes in here: rectangles, a circle, right, and a quarter circle. So we can split this plate into standard shapes and follow the approach for a composite shape in finding the centroid. If you recall, these are the equations we established in the theory video for finding the centroid of a composite section. X bar equals sum of AI times xi divided by a, and y bar equals sum of AI times yi over a. X bar and y bar are the x and y coordinates of the centroid of the composite section. In this example, the composite section is subdivided into three areas: sub-area 1, sub-area 2, sub-area 3. And in this equation, AI is the area of sub-area I, and xi is the x-coordinate of the centroid of the sub-area I. A here is the total area. There are two aspects in which we want to be careful. First, if we have a hole in the shape, we subtract the hole, and we want to use negative sign for the area of that section in these equations. Second, we want to use proper sign for xi's and yi's. In other words, if a centroid lies on the negative side of the x-axis, we want to use a negative value for the x-coordinate of that. Since the sub-areas of this composite section are rectangle, circle, and a quarter circle, I thought I'll summarize the relevant properties here. The first line here gives you the areas, and the second line here gives you the location of the centroid of these standard shapes. Step 1 is to come up with a subdividing scheme. When you do, keep in mind these points. Firstly, there are usually multiple ways to do this. In this example, I can see at least two different ways to do this. This is one way, and here I have subdivided this composite shape into this quarter circle, this middle rectangle, this left rectangle, and the circle. The quarter circle and the two rectangles are to be added together, and the circle is to be subtracted. The second way that I see here is that instead of subdividing these long rectangles into two rectangles like I have done here, you could treat that as a single rectangle. As long as you do this correctly, each approach will lead to the same final results. And therefore there is no right way or wrong way to do this. Follow the route that you feel most comfortable with. Point number 2, you want to mark the sub-areas in a clear, unambiguous manner. This is important because when you write down equations, you don't want to get confused. Hatching, like I have done here, is one way to separate the sub-areas. Point number 3, you want to go ahead and mark the centroid of each sub-area along with its coordinates. And in this example, C1 is the centroid of this quarter circle, and from the formula that I have shown in the previous slide, we know this distance is supposed to be 4r over 3 pi, where r is the radius of that quarter circle, and in this case is 30 millimeters, right? So this distance is 4 times 30 millimeters divided by 3 pi, and similarly this distance is exactly equal, 4 times r divided by 3 pi. C2, here is the centroid of this middle rectangle, and due to symmetry of this rectangle about this y-axis, we know the centroid lies on that line of symmetry, right? So C2 is on the y-axis. The distance along the y-axis from the x-axis is 50 millimeters, which is half of the height of this rectangle. The circle here lies exactly in the middle of this rectangle, and there are two lines of symmetry for both the rectangle and the circle, and therefore C3 and C4 lie in the middle of that circle. We know the coordinates of the middle, and therefore there's no need to mark them. The next step is to perform the calculations. Since we are starting on this at this stage, it's a good idea to use a table to organize our calculations. Here are the equations we're going to be using. The objective for this table is to find the numerators and the denominators in these equations, right? So we want to find the sum AIXI, the sum AIYI, and the sum AI. We have four subsections here, and for each of these we'll find the AIs and put them in this column, XI and put them in this column, YI and put them in this column, and then we'll multiply this column with this column and write down AI times XI for each of the section in this column, and the product of AI and YI in this column. Then we sum this column in order to find the area of the composite section, and we sum this column in order to find the numerator for the first equation, sum this column in order to find the numerator for the second equation. A table like this allows you to focus on each term in detail and get not only the numbers right but also the signs right. Here are the numbers. The table is fairly easy to follow. Let me point out a few key things here. Area of this quarter circle equals area of the full circle divided by 4, right? Area of the full circle with this radius would be pi r squared. So that's pi times 30 squared. So that's what I have over here. The area of this circle, full circle, is pi times 10 to the squared. But we need to have a negative sign in front of that because this represents a whole and it's going to be subtracted, right? The x-coordinate of the centroid of the quarter circle equals this distance, which is 20 millimeter, plus this distance, which is 4 times 30 divided by 3 pi. So I get 32.74 for that. The x-coordinate of the centroid of this middle rectangle is 0 because the centroid lies exactly on the y-axis. These two centroids lie on the left side of the y-axis, and therefore the x-coordinates for these two centroids are negative. So I have minus 45 for this and minus 45 for centroid 4. How did I come up with 45? Well, that's 20 here plus 25, right? 45. Put a negative sign in front of that. Now you can see all of these centroids lie on the positive side of the y-axis, and therefore the y-coordinates are all positive for them. The y-coordinate of the quarter circle is once again 4r divided by 3 pi, and we get 12.74 millimeters for that. And the y-coordinate of the centroid for the middle rectangle is 15 millimeters, and the y-coordinate for these two centroid is 15 millimeters. So at this point we are done picking up numbers based on the picture. Now you use your calculator to fill the remaining cells. For example, this number right here represents A1 multiplied by X1. So that will be 706.5 multiplied by 32.74. So that gives you this number. And this number right here represents A1 times Y1. So that will be 706.5 multiplied by 12.74. So you get 9,000.81 for that. And so on. You just pay attention to not only the numbers but also the signs. For example, this number right here represents A4 multiplied by X4, but each of these two numbers has a negative sign in front of that, and therefore the product of the two is a positive quantity. Alright, so now you sum up this column, once again paying attention to the signs. So we have positive here, positive here, positive here, and a negative here, and then you sum these up algebraically, you get this number. So that's the total area of this plate with the hole subtracted from the overall area. Sum of this column is this, Sum of this column is this. Now we simply use these equations to find a value for x bar and a value for y bar. X bar works out to be minus 9.78 millimeters and y bar works out to be 14.48 millimeters. So based on the values we got for x bar and y bar, I have marked the location of the centroid of this composite section in this sketch here.